The Earth is comprised of giant tectonic plates. They're always in motion. These movements usually take place at small intervals over thousands or millions of years. However, at times during the process, abrupt movements take place. This results in a massive amount of energy being released. The earth beneath our feet shake. We experience an earthquake. Earthquakes have no season. They occur without warning, with massive destructive potential. And yes, we react. But what really is behind these phenomena? Why do they happen? Can they be monitored? Is earthquake damage to structures and infrastructure preventable? And what of the impact on those who survive, the survivors of earthquakes? Are there any psychological impact? And can that be managed? Good evening, ladies and gentlemen. As responsible academics, the Faculty of Science and Technology, Engineering, and Social Sciences have assembled a team this evening to provide answers to our audience, both local, regional, and international audience. This session will examine a number of factors. One, we're going to look firstly at the geology behind earthquakes. Then we will take a look at the phenomena called earthquake monitoring and mitigation. Next, we take a look at structural engineering for earthquake resilience. And of course, the too often forgotten, coping with natural disasters from a psychological perspective. Ladies and gentlemen, my name is Clive Davis. I am a disaster coordinator. I am a disaster risk management specialist. I am a former Director General of the Office of Disaster Preparedness and Emergency Management, Jamaica. I currently operate as the Chief Emergency Management Officer at UWI Mona. We're all shook up. All shook up. But I am sure that by the end of this program, ladies and gentlemen, we will have a very good understanding of earthquakes, how they happen, why they happen, and ways to deal with them. The program is going to be very simple. Each presenter will have about 15 minutes to make their presentation. And at the end of that presentation, at the end of all presentations, you'll be given an opportunity to ask questions of the presenters. And so, ladies and gentlemen, without further ado, I'd like to allow you to join me in welcoming our first speaker, Mr. Kevin Tanku. Kevin is currently the head research fellow at the Earthquake Unit. He holds not only a bachelor's in geology and geography, but also a master's in disaster risk management. He's a council member, and country representative on the International Seismological Center. Kevin is also a board member of UNESCO, IOC National Tsunami Board. He's a principal researcher for the National Disaster Council and a country rep locally here. He sits on a number of boards and represents both the university and the country in many spheres. Ladies and gentlemen, this evening, Kevin Tanku will speak with you about seismic monitoring and mitigation in Jamaica. Kevin?
Thank you, Major. Good afternoon, everyone. Let me just share my screen. Okay, so today, what I'll focus on would be seismic monitoring and mitigation. And this talk would go in line with the following talk. So it's like a part one and a part two. My talk would deal with seismic monitoring and exactly how do we actually detect earthquakes and what the earthquake unit actually does. And just touch a bit on mitigation to set the scene for the application behind the sort of research and work. This would then be followed by Professor Mitchell's presentation, which again would then show the research side of things and exactly how our data can be integrated with, geology data and so on to get a better understanding in terms of our risk, as well as the different dynamics within our region. So just to give some overview of the earthquake unit itself, we are the principal or the sole body for earthquake monitoring and seismic research in the country. And we have a considerable network portfolio. And I'll just touch briefly on some of them. We have, of course, the Jamaica Seismograph Network, and this contains several sub-networks or 3 sub-networks, our short period network, a broadband network, and accelegraph network. And these are essentially different type of sensors for detecting different characteristics of earthquakes. We also operate and manage the Jamaica Educational Seismic Network, which is a series of, I would say, educational seismographs that are deployed in schools where students can utilize it to get a better understanding in terms of how earthquakes are monitored, as well as how we then process that data itself. So it sort of covers geography, computer sciences, physics, as well as the STEM fields itself. The earthquake unit also helps manage one of the Caribbean tsunami warning stations, and this is part of the bigger global seismograph or seismographic network, as they call it, which is managed by the USGS. We also maintain connections to various regional networks and global networks, seismic networks, of course, as well as we have 3 GPS observational stations, permanent GPS observational stations in Jamaica. 2 of them are offshore and 1 onshore. And interestingly enough, something that's lesser known, the earthquake unit is also the national data center for the Comprehensive Nuclear Test Ban Treaty. And this in itself is quite a considerable network, which includes more than 150 sensors across the world, which is used for nuclear, for detecting and for monitoring any sort of nuclear testing and any sort of nuclear devices also. So just to touch on some of our projects or what we actually do, currently we collect seismic data as well as geophysical data. We maintain the seismic database for Jamaica and the near region. And we also have the capacity for geophysical and geological research. We have conducted microtremor surveys in the past, and we also do seismic assessment and different type of intensity surveys. All of this, of course, we then need to represent it. So we do a lot of geospatial analysis and maintain a geospatial database as well. And something more recently would have been our hazard mapping initiatives that we are now ramping up with collaborators and risk assessments. And we also have several other project involvement and collaborations that the unit is involved with. So one of our arms of the unit is also public education and outreach. And primarily, people know us for informing the public about felt earthquakes. So this is particularly important for the authorities to sort of set up their response mechanism and sort of respond to any sort of felt earthquake if it's indeed significant enough to create any sort of chaos or damage. The unit also hosts various groups for tours, schools, and other small groups. We attend a variety of expos and different events. We also assist with lectures or contribute towards lectures in Department of Geography and Geology, as well as facilitate labs and some seminars. Of course, we participate, being in, within an academic realm as well. We participate in conferences and workshops. And one of our services to the country is we are involved with emergency operations through the National Emergency Operating Center. And we also have several external relationships that we foster, and we support various entities nationwide. All right, so now we get into the seismic monitoring. So again, we have the Jamaica Seismograph Network, and this is something that includes several sensors deployed across the island. So you'd see the green triangles on this map in the center, which represent our broadband and short period stations. And you can see images. Let me just use a laser pointer. This is one of our stations, one of our I would say one of our more recently built station. We also have various type of installations across the island. So our accelegraph network itself include free field, as well as building installation. And this is used to measure strong motion and its impact on certain sites, as well as on buildings. This, of course, is transmitted in real time back to the unit via a communication network. So we would see the picture to the center on the right-hand side. Shows us a tower over there where we tend to house or host some of our communication equipment. So in a nutshell, this is the Jamaica Seismograph Network. And of course, we are looking to expand going forward in terms of our coverage for the island, create a more dense network. And of course, this would then provide, in turn, better data, better quality data, as well as, a more detailed insight into our tectonics and our seismological characteristics of the country. All right, so what do we do when we actually collect this data? So again, it's streamed real time to our central recording station at UWI Mona campus in the Faculty of Science and Technology. And within our data acquisition phase, of course, we run it through various servers and through our network and various servers. And we then process this data. So we would see down here, we would see a seismic signal from one of the stations. We process the signal. This is then how we locate and determine the magnitude of the earthquake itself. Of course, if it's a felt earthquake, if we get a report that is actually felt, we then move on to pushing out a bulletin, or a felt earthquake bulletin. And many of you may have seen this, across social media, in the news, and on various websites and so on. But post-earthquake or post-event, we also do what we call an intensity survey or felt report survey. And this incorporates some geospatial analysis, where we then integrate this data itself with some maps, and we sort of display the intensity of shaking across the island. Okay, so seismicity of Jamaica, and I'm just setting the scene here so that Professor Mitchell would then show you exactly how this data itself is integrated into our understanding of earthquakes in Jamaica and within the region. And Jamaica is no stranger to historical events. Many of you would remember the 1692 Port Royal earthquake, but there are also other significant, or what we would consider significant earthquakes throughout the last few hundred years. And with most recently being what I'm going to show you in a bit. Prior to that, we had a near region earthquake, quite a considerable earthquake, and this was felt island-wide in January 2020. Missing a slide, so I'm not sure what's going on here. Let me just try. Okay, I'm not certain where my slide went, but I'll just continue. All right, so I initially, and again, you'll see this information displayed in Prof. Mitchell's presentation as well, but I had a slide which showing us seismicity for the period for the year. So I'm not sure what happened there. So okay, with local earthquakes, of course, we can consider Jamaica to be in a moderate to high seismically active zone. And throughout the last 5 years or so, we've recorded 150 and more earthquakes. This is local earthquakes. Of course, we measure, we record some of the near earthquakes as well, and regional, distant, as well as local blasts that may occur from quarrying and these activities. So moving on to hazard mitigation, we of course, this is a hot topic now because people want to know exactly what do you do to mitigate or to lower your risk for earthquakes. And one of the things that we actually do, or what you can do, would be your general hazard assessment and various type of geological surveys. And this would in fact tell you your risk level or your exposure level to strong ground shaking or to various secondary hazards from earthquakes. We also would look at retrofitting of existing buildings. And of course, the civil engineer and structural engineers would speak more about this. But this is, of course, one of your mitigation strategies that we would consider more of a larger investment, something that we would deem as, a more of expensive option. But of course, there are various type of retrofitting methods that one can utilize. One of the other things you can do to mitigate against strong ground shaking or earthquake hazards would be to ensure that you construct your infrastructure, your new buildings to withstand any sort of strong ground motion or shaking. And of course, we can utilize our accelegraph network or data from that network to measure, to monitor the building performance. And this is key, especially when you look at your critical infrastructure itself across the island. Another good mitigation strategy would, of course, be seismic zonation. And this is essentially looking at how we build and how we plan for the future, where we build and understanding our risk. Of course, one of the key criteria for determining your risk at a certain location would be including subsurface geophysical investigations and various type of surveys. And this is very important in identifying exactly what sort of criteria is required for your, if you're doing a building or any sort of infrastructure. Of course, you have research and development in various areas where you can look at cross-cutting relationships or cross-cutting applications within disaster management. And one of the key things that, it does not cost that much and it's something that really benefits the public would be to ensure that you have frequent education initiatives as well as awareness campaigns. So where are we going? So I explained exactly where we're at in terms of at the unit, what we do. Of course, with many agencies and different departments and so on, we all have our challenges. One of our main challenges at the unit being space. We have outgrown our current space. So this is something that we are actively seeking to see if we can get relocated to a larger space which would allow us to more effectively manage our data center or to setting up our data center. We also have some challenges with procurement and the length of time, especially when it takes, when a seismic station goes down, we need, equipment urgently if we don't have spares. Staffing, of course, so we're looking to grow the unit. There's a lot of potential, again, for multidisciplinary studies. And funding, which is, again, one of the more common sort of challenges. But we also have a significant risk profile, especially when it comes to our seismic stations and when it relates to exactly what we have in the field and larceny, vandalism, and these things here. In terms of operations and what we do going forward, we are looking at developing a tier 3 data center. This would be our active operations center for responding or for monitoring earthquakes as well as tsunamis and other hazards. And this, of course, requires some redundancies. So hence we are proposing, to sort of move towards that direction where we have redundant systems in place. And one of the areas that we are excited to venture into would be the capacity to now look at microzonation surveys. And recently we would have received some funding to provide equipment and training So we are very excited to see exactly where this takes us in terms of our scope and what we can do and contribute. Of course, subsurface investigations, we can incorporate some of this equipment into that. And strong ocean research. This is, of course, an untapped area, and I think it has provides a lot of opportunity for studies, especially with the engineering community. But ultimately, we would like to have a short-term warning system in place. Of course, this would provide rapid alerts to critical infrastructure and to various critical, I would say, facilities across the island. Geotechnical analysis, which again would be something that's required for how we exactly how we build and how we determine your site characteristics. And then, of course, modeling and machine learning as we train our software and our applications to actively look for earthquakes and to be able to detect them better. So for collaborations and opportunities, feel free to contact us. I have the information on the next page, but we do work with several other agencies as well as regional and international partners. So we are open for collaborations, and we do have several areas that we would like to explore, again, cross-cutting sort of scope. So I'll hand over back to Major, and Prof. Mitchell will then take over where he show you how exactly this data is incorporated and what we know from this data now. So if you feel an earthquake, here's a QR code. You can scan it and you can go to our intensity form. And this is where we can actually get some information on your experience. This helps us. So thank you very much.
Hi, thank you. Thank you so very much, Kevin. Ladies and gentlemen, you just heard from, our head and research fellow of the earthquake unit here at UMona. It was a very interesting overview of the earthquake unit, how it operates. He spoke about the network, the seismic network that we have across Jamaica. Importantly, the seismicity of Jamaica, and I'm sure that Prof. Mitchell is going to delve a little bit more into that, because we need for persons to understand that this is our reality. And so it was very timely that Kevin took his next side over and looked at the whole matter of mitigation. What is it that we can do better? The fact that we're here, the fact that we have this level of seismicity, the fact that we have this level of earth movement taking place, what is it that we should do better? How can we better protect critical infrastructure? How can we better protect schools? How can we better protect homes? And so at this time, ladies and gentlemen, let me just say thank you so very much to Kevin Tanku. I'm now going to make way for a presentation which is supposed to be telling us a little bit about fault systems in the Northern Caribbean and Jamaica and the risk of earthquakes. Professor Simon Mitchell, he has been mapping geology in Jamaica for nearly 50 years. I'm not sure how that works out because I'm sure he's not yet 50, but let's move on from there. He got his PhD in Liverpool in the UK, and then took a position here at the University of the West Indies. He currently holds a chair as the professor of sedimentary geology. His diverse research interests includes, a whole range of issues in geology, inclusive of his many publications that he has done. And Simon Mitchell is always in demand as a speaker locally, regionally, and internationally. And so, ladies and gentlemen, please allow me and let us welcome Professor Mitchell as he speaks to us on fault systems in the Northern Caribbean and Jamaica and the risk of earthquakes. Prof. Mitchell?
Hello, yes, the program at the moment is not loading, which is quite interesting, but we'll work around that as soon as I can work out how I do that. But yes, so Kevin mentioned.
Prof, sorry, one thing. I don't know what happened to the map, but I have it here. It probably will set the scene while you look for your stuff. If you mind, I can share it.
Okay, yeah, put it up while I try and work out what's actually going on at the moment, because it's not actually quite working at the moment. So yeah.
Okay, so yes, here is our map for annual seismicity. And this is what Prof. Simon is going to speak about in a bit here. And we could see a strong distribution of a large number of earthquakes to the eastern part or eastern portion of the island. And we can see those three significant events for the year, which is a magnitude 4.9 in April. We also have the September earthquake and the last week earthquakes with aftershocks as well. So back over to you, Prof.
Yeah, I'm not finding it yet, so I'm trying to. Zoom seems to have disappeared somewhere. So, okay, I don't know where it's gone, which is very strange. Now, let me remind you that this sort of work is not single people. Although my mapping is a lot of me, it's not just me; it's other people as well. And people in the earthquake unit also produce a lot of this information. So when we actually look at the actual fault solutions that I'm going to show you, this is coming from people in the earthquake unit. So you've got to see that where it says presented by Professor Mitchell, it says presented by, and there are other things there and other people are involved, and they won't all be acknowledged. And I apologize to any of them. That's the situation. But have a look at this. This is the earthquake. This is the earthquake that all of us got very upset on. And it says 8th of November. It shouldn't be 8th of November. Okay, for the earthquake anyway. But what you can see there is a big earthquake. And that is what our problems are. And you can see that it's highlighted there. There's P waves and there's S waves. And we use them to tell us something about it. But if you look at them, they're not that big. The big ones are the other ones after what we call the body waves, Love or Rayleigh waves. They have different names. Those are the ones that cause more of the damage. And when we feel an earthquake, you often feel a little jolt to begin with, and then something else happens. And that's because these waves travel at different speeds. So when they get to you, they get to you. So in other words, if it's nearby, you're going to see these two, different things getting to you very, very quickly. So you might only feel one thing. If it's a long way away, you'll feel more than that. So the real thing to think about is, okay, if I feel one little jolt and then it gets bigger, it's probably further away and it's probably not such a big problem. It could be a big earthquake, but it might not be a problem for you. But for some of these other things, it can be a problem. So what I really want to do is to go through and tell you why we have the risk of earthquakes, and then to actually show you what that is a problem for us. I got a little bit of physics, but I'll try and do it nice and easy so that perhaps people can understand. Then I will show you the earthquakes that we have happened or have happened in the last half year. And then I'll say what I think might be going on, which might be good, but it might be bad. So if we look at things, we sit in the Caribbean, okay? And the Caribbean plate is a distinct plate separated between North America and South America and the Pacific. Now on this, I've also put the Atlantic plate, or the Atlantic in inverted commas, because the Atlantic's actually touched to North America. It's attached to North America and South America. There's no boundaries there. So when we actually look at these things, we can actually work out where the actual plate boundaries are. And you do it on two things. First of all, you do it on where volcanoes are. And the volcanoes are the little triangles sitting in the east and in the west. And so it's sitting in the Lesser Antilles and the Central American region. But also on top of it, bigger than that, is the earthquakes. And you can see the earthquakes go around these areas, a bit diffuse in the south, but along the north, it ends up as two zones. So there's one zone that goes through northern Hispaniola and then goes south of Cuba and meets at a spreading center. There's something that's a spreading where we actually have new oceanic crust produced. And the other side of it, the southern side, comes through Hispaniola and then into Jamaica. And that is the one that causes more problems because that comes directly through us. Although saying that, you see the blob that's just to the west of Cuba, that was a big earthquake that actually caused people in Montego Bay considerable stress because they felt it. So big earthquakes elsewhere can be felt. So we zoom into that zone, and this is what it looks like. And this is one off the internet, which you can download and have a look at. And so you got really two fault systems. You got one north, the Orient fault system that goes septentrional fault system. And you got one at the bottom, which is the Walden fault system that comes into Jamaica, not easy to follow, and then goes into the Ranquiro Plantain Garden fault system. That is the one, that bottom one is the one that causes us problems, because that is the one that comes directly into Jamaica. And if there are big movements on that, and these earthquakes, these three big earthquakes that we've all felt this year, are on that fault zone. And so that really is significant. And that is problematic for us. And what we need to do is to understand it. And you might remember that we've had two very big earthquakes in Haiti in the last 13, 14 years. So we have to be very, very conscious of these things. So I thought I'd just do, well, what I do is I walk across Jamaica. I drive across Jamaica. I collect loads of information. I work out what the geology of Jamaica looks like. That's very simple. But what this enables me to do is to work out where the different fault lines are. And when I can work out the different fault lines, I can also work out using what earthquakes have happened over the last 50 years or so. I haven't been here 50 years, by the way, Clive. So I've only been here 30 years. So. But we can work out really which are the active earthquakes, or which are the active faults. And that is a valuable thing for us to do. So if I plot that, I can show you where where the active faults actually sits. So if you look on the right, you see PG, which is the Plantain Garden Fault. It comes in and turns up. And it actually turns into the Blue Mountain Fault. We won't worry about that too much, although we will have to actually see that later on when we talk about the earthquakes. But the length of faults is very important. The longer a fault is, the greater an earthquake can occur on it. So what we have to do is we have to say, okay, the longer faults are more problematic. And you see the longest fault there is that South Coast Fault, the SC, which is down at the bottom. That's probably our biggest issue. That is probably our biggest worry in terms of something in the future. You want to go and look at it? Well, yeah, most of you know where Manchester is. You go up there. You go to South Manchester and you look down and there's a dirty grey big drop as you're going into the ocean. You go into St. Elizabeth and look down at Lover's Leap, same thing. Why? Because that's a fault. You go to you go into Manchester and you go down and there's Spur Tree. Why Spur Tree there? Spur Tree is a fault. So lots of these topographic features are active faults, and the reason they're topographic features, they're hills or they're cliffs or whatever they happen to be, is because they are faults. And they are therefore very active. And that is one of our problems. Kevin talked about movement of things. And one of the things we do record is the movement of Jamaica. Now, when you go out and driving and you're out there driving and you're driving around and things, you use GPS systems to tell you where you are. But what we can actually do is use much more detailed GPS systems to tell us how much Jamaica is moving. But more importantly, how different bits of Jamaica are moving. Now, you look along that. You look at those arrows. The arrows are longer in the north and the east, or the northeast, and they're shorter in the south and the west. And so what that is picking up is how Jamaica is being changed in shape. Okay, so Jamaica's being changed in shape. It's being squashed from the northeast to the southwest. You notice the little keys down the bottom, okay, Morant Key and Pedro Key are moving in a little bit of a different direction at a much less speed. So what you're actually seeing is that Jamaica's being squashed. And that squashing is what gives us the earthquakes, because that creates stress to build up on our faults. And when those faults move, it causes a problem. And I've just put in there's two things. So we're getting a squashing in one direction, which I'm calling sigma 1, and the opposite to that is sigma 3. The other one is down through the middle of Jamaica, which I haven't put on there. Okay, now we get to a little bit more of geology and things. So if you do that same thing and you squash Jamaica, what happens? Well, you get folds, and the folds will relate to the direction, well, are perpendicular to the direction of squashing. So the folds are north, west, southeast, and then you get faults. And there are east-west faults up the top because of where we sit on the Caribbean plate. And there are normal faults, which don't tend to worry us, and reverse faults, and the reverse faults worry us as well. And so the reverse faults are also northwest, southeast. So a lot of the structural features in Jamaica are in that direction. So I just thought, well, let's look. Okay, so let's put one of these east-west faults on. So, or several of them, in fact, and let's just look at what goes on if we look at that. Okay, so that's the sort of thing we're seeing. We're seeing bigger movements on one side, smaller movements on the other side. So what does that mean about that actual fault system? I'm looking at the South Coast Fault there. And the reason I'm doing that is the biggest one. I think it's more concerning. And what it tells is that, well, the fault can move ineffectively to the left. So it can move off in a left direction, which we call sinistral. But also because there's a component that goes south, it can go up. So that's why you've got those high cliffs along Manchester and along Lover's Leap in St. Elizabeth. So what all of that is telling you is that over the last few million years, maybe 4 million years or so, this is what's gone on, and this is what's given us the topography, the hills, the cliffs, and everything that exists in Jamaica. And so it might not be a great amount. It might be 5 millimeters a year or so. But over time, that actually builds up to build stress and change the shape of Jamaica. So what do we see? What are our features? What are we seeing here? So we call it transpression because it's basically it's a fault with uplift along it. It's an east-west fault with uplift along it. Well, east-west faults, they show the significant uplift. I've mentioned them already, South Coast, and Lover's Leap and that sort of thing. That's the big one. That's big. Has it moved? Not recently. Is that a concern? Yes. You go down, you drive down Spur Tree Fort. You spur down Spur Tree Hill. What is a fort? That's all been uplifted. Anybody want to guess how much that's been uplifted? That's hundreds upon hundreds of meters. So you're actually seeing there the results of these faults. And every single time that moves, and that's a still active fault, that will give you a significant earthquake. We have ramp valleys. In the past here, they've been called grabens. People talk about the porous graben. It's not a graben. A graben is an extensional feature. The porous system is a compressional feature. The rocks towards the northeast are going up, and the rocks towards the southwest are going up. And so you get a valley. Is that just significant for earthquakes? No, it's not, because that also controls where the water flows. So those sorts of things are important in understanding our water resources, particularly as we go forward to climate change. And then we get to flower structures. A flower structure is a strange thing. I mean, they're named after flowers. So you got a flower and like a rose, and it's sitting there with all its petals sitting there in that way. Well, basically, what a flower structure is, things are being uplifted, and they can be downlifted as well. But in our terms, they're uplifted. They're positive flower structures. And what that basically is, the uplifting of these things, and that drives significant uplift. So, Central Inlet is going up a bit. The central part of Clarendon is going up a bit. Northern Clarendon is going up a bit. But the Blue Mountains, the center of the Blue Mountains, is going up at the greatest rate anywhere in Jamaica. And that's recorded at 2 millimeters a year. It doesn't sound much. But if you put that over 100 years, 1,000 years, that starts becoming significant. So I just plotted a few of these things to show where some of these things are. This is so this is the geology of central Jamaica, central southern Jamaica. There's a thing there called the Central Inline, which sits in the north, and you can see there's folds there. And I didn't mention the folds, but there's folds in there. But you can also see there's many other things. So the Manchester Plateau is uplifted, and that's uplifted on 2 faults on either side. The Brazaletta Mountains is the same thing. So what you've got is they've got a lot of deformation that goes on there that actually gives us the actual patterns we see, the geographical patterns we see across Jamaica at the present time. This is a little map we put together on a paper we published, which shows eastern Jamaica and actually shows the uplift there, this flower structure, and the little lines with the triangles on them are the thrusts, they're going up. So on the triangle side, that has gone up. And what you can see is the center of the Blue Mountains is going up, and everything around it mostly is going the other way. So that is what is driving the Blue Mountains up. So you've got movement from the east along the big fault, the Plantain Garden Fault, which I can probably show there. So that's the Plantain Garden Fault. And so this side is being compressed against this side. That fault curves. And therefore, if you try and push it in that way, it pushes the Blue Mountains up. Now, why is that significant? Well, all the earthquakes that have happened this year, the big ones, are on those fault systems. They're either on close to the Plantain Garden system, or they're on the faults that come off it. So what we've seen this year is the Blue Mountains flower structure, if you like, being pushed up. That's what we've actually seen. So what are we seeing? Okay, so we saw a 4.8 magnitude earthquake in St. Thomas, 15th of April. We saw a 4.9 on the 29th of September in Portland. And then finally, of course, the one we're all remembering is the 5.6 in Portland on the 30th of October. And I think probably everybody remembers when that one was, just coming up to 11 o'clock. All of them were associated with aftershocks, but a lot of the aftershocks are small, so we can't actually solve them. So when Kevin goes in and he works out solutions to these things, we don't get solutions to every single one. So I'm just going to now show you the solutions to some of these things and actually show you how they actually work out. So this is what happened in the first one, which is the St. Thomas one. And so the bigger circle is the first earthquake, and the little concentric things are where it happened. And then you can see all these others going afterwards. Kevin didn't tell you about what these things mean, and I'm not going to tell you what they mean, but they mean things, these diagrams, they actually mean things. But I don't think we've got time to talk about that. But what I think you can see is that all of those centers sit close to or nearly close to mapped faults. So what you're seeing in there is you're seeing that the first big fault moved, and it wasn't actually on the Plantain Garden, it's south of it, it's on a fault south of that. And then all the other faults adjusted to that. And so that's what the aftershocks are. The aftershocks are other faults adjusting to the first fault. So that's that big one to begin with. We then move on. Well, we've only got the main one, this one, but again, it's right on one of these big faults, which basically sits in the front of the Blue Mountain uplift. So the Blue Mountain flower structure, it's sitting on that. And then we go to the last one, which of course is the one we're all concerned about. It looks like it's a fault that's actually not an uplift, but it's a strike slip fault moving up towards the northwest. But again, it plots right on a fault, and then the adjustments afterward, the aftershocks, the ones we've actually solved, or Kevin solved, actually show you what's actually going on. So you've got the whole of the Blue Mountains adjusting because we've had this big earthquake. So that leads you to the question of what next? Okay, are we going to see more? Well, we are obviously going to see more faults moving, and we're going to see more earthquakes. We sit on the northern boundary of the Caribbean plate. But one of the possibilities is that what we've seen at the moment is this flower structure being uplifted. And that might actually stop, and we may not go further, and that might just actually end and we won't see more earthquakes. The alternative is that this stress has now been transferred to other faults. So the Cavaliers, Cruel River, Rio Minho fault system is one that goes through central Jamaica, and it's been active in the past. It gave the 2005 earthquake. The South Coast fault is my biggest concern because that's a much longer fault, and that could see much larger earthquakes and could generate a 7 or even an 8. So my concern is that if we have seen stress transfer to this, we could see a movement on that fault zone. I can't predict it. Nobody else can predict it. It's not possible at the present time. Although I will say that we saw faults move in Haiti, in eastern Haiti, then in central Haiti, and now we're seeing the move in Jamaica. So we're seeing fault movements move towards the west. Should we be concerned? I think we should be prepared. Remember, these things don't happen every day, and there may be many years between them happening, but we have to be prepared. And being prepared means that we build in the right way, and we teach our people here to react in the right way when an earthquake happens. Maybe that's not quite what you wanted from me as the last actual slide, but that is where I will leave you at this point.
You know, despite being a student of geology, geography, disaster risk management, every time, you know, I hear Simon speak, especially about earthquakes, I have to pull my bootstraps up a little bit more. Ladies and gentlemen, we're all shook up. We got introduced, and some of us reintroduced to the Caribbean plate. The fault systems that exist that impact Jamaica, one running in the north, the one running basically right through us. We got introduced to the fault lines which exist in Jamaica, many of which we can see based on the topography of Jamaica. Simon reminded us that in many cases, fault lines equal vulnerability. It is interesting, though, to note that he concluded on what next? What can we expect next? Ladies and gentlemen, it's real. We live in an area which is seismically active. We have had earthquakes. We have had earth movements, and we're going to continue to have them. He has expressed some concerns for some particular areas, and I think we all should be concerned about them. Already, I'm getting some questions in the chat. Kevin, you're going to have to answer some of them in a little while. People are asking about, the last quake. How many aftershocks we got? Are the aftershocks still continuing? How long will they continue for? People are asking questions about the release. Is the release good or is it bad? Is it that it has been released from one fault to another? Or is it that the release is so good that we will not have another big one for some time? But we're going to hold that for a bit. So, ladies and gentlemen, after all we've heard from, yes, those two, Kevin and Simon, yes, that might have been that was the real side of earthquakes. And it was probably dark for some of us. But all is not lost. All is not lost. we have an expert here who's going to be telling us a little bit about structural engineering for earthquake resilience. The fact that we live in an earthquake zone means that we can build for earthquakes. Dr. Nicholas Morris is the Deputy Dean of Research, Innovation, and Industrial and Commercial Relations, and the head of Civil Engineering Program in our Faculty of Engineering at UMona. He's a registered professional engineer in Jamaica and in the state of Maryland, USA. He has more than 23 years experience, industry experience. Got his PhD at the University of Maryland, and his research interests include non-destructive testing of concrete, sustainable structural material, and seismic rehabilitation of buildings. Locally, he's also, well, recently, a member of the Professional Engineers Registration Board. Ladies and gentlemen, let me present to you my colleague and friend, Dr. Nicholas Morris, to take you through structural engineering for earthquake resilience. Nick? You appear to be muted, Nick.
All right, unmuted now. Good afternoon, ladies and gentlemen. Good evening. Thank you for joining us here today. Thank you, Major Davis, for that introduction. Today, we'll be looking at structural engineering for earthquake resilience, and we're all particularly interested in this because of what happened last week, Monday, October 30th. I was actually teaching a class on lateral loads, and I started to feel the shaking, and I quickly realized that I was in a one-story building with a light roof, and that had masonry walls that probably had all pockets filled. So I made haste and got to the reinforced doorway. Not all doorways are equal, and stood there past the students who were scampering on the tables and so on. Even though I was furthest from the exit, I got there with the silver medal intact, and then we decided to usher all the students out to a safe space and proceed on to the emergency meeting point for these situations. So, achieving the right amount of resilience in structures potentially subjected to strong earthquakes in their design life is an ideal but a difficult goal, and it's because of the inherent uncertainty of future earthquake activity and the pressure to reduce costs, especially for conventional buildings. So we'll be looking at structural engineers and their role briefly. We'll be looking at seismic forces and how they're considered with a mild canter through the design process. We'll be looking at the National Building Code. We'll do a gap analysis of our construction process. And we'll look at a sampling of how our Jamaican structures performed as well, and we'll taper off with some non-structural aspects of the seismic response. So what do structural engineers do? Well, we're primarily responsible for safely transmitting building or structural loads through the structure and to the ground and to the foundations, where we partner with our geotechnical engineers to ensure that the soil or the supporting ground can take the loads. A good analogy is we're the bones and muscles of your body, right? We're responsible for, well, your body is a mobile object. Most structures are static, but responsible for resisting most of the loads that you might see. So in the image here, we see the raw structure of a building. Nothing else is present, and no architecture, no mechanical, electrical, plumbing, nothing else. So everything else, all the other disciplines to a structural engineer are considered a load. So how are seismic forces considered? Well, we'll begin where all engineers should begin, and that's with the building code. A building code is a legal document that guides how the design process should be considered from conception through to construction. Our building code JS 306 was enacted in January 2019. Then we'll look at some peak ground accelerations. You all are familiar with the Richter scale. We'll look at building categories. All buildings are not required to be equal from a design standpoint. We'll look at the design philosophy, life safety versus immediate occupancy, and how we determine the controlling design lateral force. And we'll finally look at the geometry of the structure before we get into other things. So the building code is all building professionals are required to adhere to the building code, and the building code heavily relies on the International Building Code, which is a good thing. International Building Code, IBC, latest rendition of 2021, is a mother code, and it refers structural engineers in particular to several subordinate codes, beginning with the American Society of Civil Engineers, Code 7, last rendition 2022. And that tells us about loads, especially seismic loads. And then there are several other material-specific building codes that have guidance on seismic design and so on. So we see the American Concrete Institute code here for reinforced concrete, the steel, structural steel manual and code in the rear. And then we see the code for masonry and the code for timber. And they all have design considerations. You're all familiar with Richter scale, and the Richter scale, just to remind you, is a logarithmic scale. So each gradation on the Richter scale is a factor of 10 of magnitude. So a 7 is 10 times as powerful as a 6. That's just the energy release, though. Engineers are more primarily interested in the accelerations of the ground and the structure in response to the ground motion. So here we see two spectral response acceleration maps for Jamaica. The spectral accelerations are an inertial response experienced by a building of a particular period. It's important to remember that in a seismic event, it is a ground that is moving, and the building moves as an inertial response to the ground motion. So there are two spectral acceleration contour maps for the Jamaica, one for short period buildings, roughly 0.2 seconds, and one for a 1 second period building. Of highs of 73% of the acceleration due to gravity. That's in the Blue Mountain area, as Prof. Mitchell would have shown you. And then for the 1 second period building, 30% of gravity. So that gives us a starting point to determine which of the seismic load analysis procedures we can use, and the increase in sophistication in these three tiers. We can do a static approximation and computer model that, or even do it by hand. We can do a modal analysis, which determines the period of the building more exactly, and also model that in computers. Or we can determine a site-specific response spectrum, where we partner with our geotechnical engineers to determine what are the spectral accelerations at that particular site. Then we have to determine what the building categories are. Not all buildings are required to be designed to the same level. There are Roman numerals 1 through 4 here, and category 1 is essentially a building that doesn't have a substantial use risk to life. And so a barn that's housing hay, we don't have to worry about that too much. And on the opposite end of the spectrum, we have critical structures that have to remain operational during and after an earthquake. An air traffic control tower comes to mind. Planes will have to land after the earthquake. So that is a much more critical category and has a higher risk factor. The risk factors are associated with the importance factor. And if we look at our category 4 buildings again, we see our importance factor is 1.5. And what this essentially means is that we're bumping up the seismic loads by 50% when we're considering these types of structures. In dealing with earthquakes, we have to recognize that dealing with the maximum considered earthquake, which is what we're designing for, but have to recognize that failures probably will occur. And so we redefine failure to permit certain types of behavior that would be considered failure under different regular loads. Yielding, for example, where we can take advantage of the plastic region of the deformation of steel, structural steel, or reinforcing steel. And one recurring lesson that results from forensic engineering after earthquakes is the importance of structural details. How you actually detail specific areas of your structure, how you detail the reinforcement, or how you may detail the structural steel, whether a bolted or a welded connection. That's critical for the seismic response. Our design philosophy leads us to try to determine what is the performance level that we're trying to achieve. For our air traffic control tower, which has to remain fully operational, we're dealing with a maximum considered earthquake. that has a 2% probability of exceedance in 50 years. And you shouldn't read that as, oh, well, 50 years ago was 1973. It really, the statistics and probability that's applied to that deals with a return period of 2,475 years. We also have to, because we live in Jamaica, we're subject to seismic forces and we're subject to hurricanes as well. So we have to determine which is the controlling design force that's going to dictate how we design our lateral force resisting system. Unless you're an engineer that lives in England, well inside a tectonic plate and not subjected to hurricanes, maybe your life is a little easier. Just to back up, we usually use the base shear as a comparator to decide whether we're going to use wind or seismic as the lateral force that we're going to consider for design for the lateral force resisting system. There are different types of lateral force resisting systems that we can employ to resist our lateral loads. And we start with moment resisting frames. Inherently, concrete beam and column connections, when poured monolithically, are moment resisting frames, and they have lateral resistance capabilities. If we're using structural steel, we may want to use braced frames, and we can use shear walls in combination with many structural materials. In all cases, the lateral force resisting system is contiguous from roof to foundation level. Doesn't mean it can't have openings, it just has to be consistent from roof to foundation level. We also are required to combine loads. We have to look at the combination of dead, live, lateral earth pressures together with our wind and our seismic loads. But it's important to note that the maximum considered earthquake and the maximum considered hurricane are never combined if you scrutinize the combinations. And I have a running joke with my students that maybe that's time to get your Bible. So the geometry of the structure, and I want us to take a pound of salt when we're looking at this slide, because I'm going to be speaking in generalities here, whereas the design of structures is a bespoke activity. So generally speaking, under seismic loads, short and stocky buildings perform well if they're designed properly. Having a lightweight roof is a benefit. Flexible structures are better suited for seismic loads, and well-detailed joints and connections that provide ductility are also suited for seismic loads. Generally speaking, with a pound of salt for wind loads, rigid structures perform well, flat roofs are beneficial, and slabs are also good as well. Slab roofs, that is. Low-rise buildings obviously perform better, and in planned square and octagonal shapes perform well. Open structures obviously attract less wind loads. So good structural design is, among other things, a balancing act between rigidity and flexibility. So how robust is our building code? It's very robust because we have collaborated with the International Code Council, and we're leaning heavily on the International Building Code. So this aligns us with international standards and prevents us from reinventing the wheel. Consequentially, we're using those codes those codes are subjected to continuous improvement, strong research foundations, and a large amount of supplementary material. So we can rest assured that our building code is robust. So where are the gaps? Because, you know, we live in Jamaica, everything is not a bed of roses. So here are some suggestions for improvement of the construction process. From the designer's standpoint, we should all be registered with the Professional Engineering Registration Board, that's PERB. We should all be engaging in continuing education, like this forum here. We should all take the effort to learn the building code and the IBC and its subordinate codes. And good advice is to stick within your discipline. If you've been designing roads for 15 years, it's probably not a good thing to, even if you're a civil engineer, it's not a good thing to switch to designing a 15-story building. We also want to consider detaching non-structural walls. More on that later. Contractors should probably employ or contract registered engineers, or they can train young engineers on the path to registration. And please, contractors, no more cement bags in our masonry walls. I'll let that image speak for itself. From the side of the local authorities and the government, we should enact the revised Professional Engineers Registration Act. that will mandate continued education for registered engineers. And we have also changed the terminology, not engineers anymore, because any and everybody is calling themselves an engineer nowadays. So it's registered engineer. Local authorities should employ sufficient numbers of registered engineers within their specific disciplines for detailed review of these specific projects. Or maybe you could contract registered engineers to review the projects in their discipline who are not associated with the project. Maybe you could incorporate a fee into the approval fees for this. Just a suggestion. And it's about time. I know a lot of my consultant colleagues may not be happy with this, but it's about time that at least for category 3 and 4 buildings, we should be required to submit design calculations along with drawings and specifications. It's also about time for us to require a professional engineering exam for registration. In California, which is subject to high seismic loads, there's a 16-hour, 2-day professional engineering exam for structural engineers. 8 hours on Friday, 8 hours on Saturday. And you do gravity loads on Friday, you do lateral loads on Saturday. So you can't come out of that exam unless you know exactly what you're doing. From the client standpoint, clients and developers really should be engaging professionals, and individual clients beware of building plans listed on light posts. So how did our Jamaican structures perform? Reasonably well from what I've seen and heard. So we're looking here in the library at, and we're going to be focusing on that column in the center of this image. This is a 1-story building with a slab roof and has perimeter columns inset from the outside perimeter. There are no shear walls on the outside. Moment frames are what is employed for the lateral force resisting system. Well, that doesn't look good. So that looks like significant cracks in the top of the column. Obviously, when the diaphragm when the diaphragm wanted to move under the seismic loads, it's going to introduce bending moments into the top of the column. Movement is to be expected in a seismic response, right? And concrete is expected to crack. It's actually part of our design calculations. But I decided to look on the roof of the building where there's some upstand beams to see what the condition of the beams and the slab is that are framing into the tops of these columns. Because if this column was so cracked, then there should be cracks in the beams and the slab as well, high moment regions. But there weren't. So I spoke to my colleague, Mr. Atkinson, and said, let's chip away some of that loose material and see what we're really looking at. So to achieve the mild stucco finish on the exterior of the column, a heavy layer of rendering was used. And it's a rendering that cracked with the slight bending and movement of the top of the columns. So some cracks are just rendering cracks. The crucial part of the column for collapse prevention is the shaded area in this circular column here, and that's inside the reinforcement. So that if the cage of the reinforcement is still holding together the core of the column, there's still a significant amount of strength left in the column. The column ties, stirrups, links, if you may, play a significant role in this to keep the column core intact. Discrete ties, if they're properly spaced, can work well, but spiral ties are even better and are mandated in high seismic regions. That can lead us to our strong column, weak beam ideology. And that doesn't necessarily mean weak beam. It just means that the beam will go plastic and the columns will remain strong. That's a good thing for collapse prevention. Here we see another, here we see a non-structural wall participating in the seismic response. Looks alarming, and it has a typical diagonal crack that suggested it was loaded under heavy shear. We measure the thickness of the wall. This is primarily a wall that's separating this foyer area from the bathrooms that are beyond. And if we look closely above the doorway, we can see the beam, the main structural beam. It frames into a column at the right side of the doorway, and come to the left of the wall, there's a column on C. So that's a moment frame that was moving as it's supposed to in response to the seismic activity. The wall was measured at 5 inches thick, half-inch of rendering on either side, so it's a 4-inch masonry block wall. It also had several electrical boxes embedded in the wall, which further compromised its strength. This wall is not designed to receive seismic loads, but it's built flush against and probably positively connected to the building frame. So it received the seismic loads. Under the strength of the beam in the top right corner, we can see the wall crushing against the beam and the diagonal crack forming from the top left corner. So this is a cosmetic repair. Looks alarming, but it's a cosmetic repair, and it doesn't compromise the strength of the building. And here we see another classic example of load reversal and shear cracks in a non-structural wall that's participating in the seismic response. We can see the massive column, brown column here, frames into a beam that's in the ceiling over to the left with another massive column that's forming the moment frame, which is the lateral force resisting system. The wall is built flush up against the moment frame, and essentially it's in the way. So it also has large openings which provide weak points and stress concentrations at the top corner. So when the building moved to the right, the first crack was formed. And then when the load reversal took place, the second crack was formed, and we get the perfect X. This is a classic example. But we love our masonry walls. We love our block and steel. Jamaicans don't want to build with anything else but block and steel. It's bulletproof. Right, so it does add a little more rigidity to low-rise buildings, but it's not always necessary, and it can increase the cost. In most situations, it's just a separator of space. So other materials can be investigated to achieve that same purpose. And in many cases, all the pockets of the masonry wall are filled. And that creates a semi-rigid wall that's not designed for the seismic loads. We can see an illustration of the concept I'm trying to get across. So we did some research on this in 2019, and we're proven that, you know, the infill masonry wall does increase the stiffness of the structure, but that also means that you're going to attract more load, right? If you try to be too rigid in a seismic event, you're going to have to resist the forces that the structure is going to see. Remember, it's an inertial response. Also, you're increasing the mass of the building. Right? Being an inertial response, more mass means more loads. So this translates to a wall that is not designed to resist lateral loading, that is experiencing lateral load. The wall is going to crack, and you're going to have to repair it. So, but more critically, you can change the designed load path of the lateral force resisting system and redirect load in places it wasn't intended to go. Right? And that can also lead to torsional eccentricity of the building. That means that the building could possibly twist under seismic load. Torsional eccentricity is limited to 5% by the code, and is frowned upon, loosely speaking, by the code. So we need to find a way to disengage or favored in-plane disengage or favored walls from the in-plane contribution. How do we do that? Well, let's look at the bottom right image first. That's the frame behaving as it should, right? Lateral load to the frame, and the frame is deforming as it should, as a moment frame should. And so what we need to do is introduce a gap so that the frame has the opportunity to move, right? And the wall doesn't get crushed by it. If it has to be a load-bearing wall, we can loosely connect it to the beam, so it can operate in compression, but the frame would still be able to move left and right. Our third case shows the situation that we're seeing in the previous pictures. So part of the research asked a couple of engineers what the potential solutions could be, and here are a couple. We could introduce a dowel that connects the wall via a slotted connection that allows in-plane movement. Here's a slotted connection that allows in-plane movement of the wall, so it's not going to participate laterally, but restrains out-of-plane movement. Remember, these same walls, if they are exterior walls, have to receive the wind load on the building to transmit it to the rest of the structure. So they have to be fixed out of plane. It's their in-plane contribution that we want to detach. This is relatively inexpensive and easy to install, and it can be installed prior to casting the upper floor and beam, or even after, through drilling through and down into the masonry wall. Here's another suggestion. We could introduce a C-clamp, and the principle is the same. The channel is going to allow the wall to move in plane, therefore not participating in the seismic response, but it restrains it out of plane. So those are two possible suggestions. Another code, the American Society of Civil Engineers 41, last revised 2017, deals with non-structural evaluation of building contents, and it has 3 tiers for structural evaluation, but I want to focus on the non-structural performance levels. So here we see typical non-structural damage. Ceiling has fallen, light fixtures have fallen, a lot of broken glass. You could be trying to exit this building or get to a safe space, and something fell and hit you and prevented you from safe egress of the building or getting to a safe space. This is a concern. There are simple ways to mitigate against this. Light fixtures should be restrained independently from the ceiling frame system and via either 4 wires or 2 diagonally opposing wires. The ceiling frame also should utilize those diagonal wires. Tall cabinets can fall, block your office door, prevent you from leaving the building safely, or fall on you, right? So if they're above a certain aspect ratio, then we need to either unite that to reduce that aspect ratio or restrain them against the wall. There are other non-structural items dealt with by the code that can be dealt with. We did an evaluation of the Faculty of Engineering building in 2018 to see whether it was compliant or not non-structurally, and we found some of the same issues that I just described of non-compliance, right? Tall cabinets in the way, and light fixtures that were not properly restrained, as well as a couple other things. We tallied up the numbers, did the numbers, and recognized that the cost to repair this, labor and materials, is relatively small compared to the 50, sometimes 70 people's safety that are in the building at any given time. So this is low-hanging fruit. So in summary, we need to be prepared for the maximum considered earthquake, as Professor Michel warned. We were all warned last week, Monday. We should stick by ODPEM guidelines, but maybe if you're in a 1-story building with a light roof and has strong structural walls, you can get to the doorway. Remember, not all doorways are made equal. You need to engage structural engineers. This is not a time to be seeking a bargain with life safety. I want you to inspect your own personal space for egress, that's exiting the building, cabinets, fixtures, or maybe an engineer can help you utilize ASC 41 and its non-structural compliance. Maybe we want to disconnect masonry walls or consider different materials or design for it. We definitely need to improve or review and inspection aspects from our authorities. I think we should try to get the revised PERA Act passed and implemented, and it's time for us to consider the professional engineering exam. One last final point on evaluations that have taken place of buildings. The clients or authorities rarely retain their construction documents, and that leaves us in a pickle because we're not able to comment on the future performance of a building because we maybe didn't design it and we don't have access to the construction documents. So we recommend that clients retain their construction documents when they can. So all we can really pronounce on is whether the lateral force resisting system is intact for whatever the force it was designed to withstand. And whether that's up to code, we don't know if we don't have the documents. Thank you.
Ladies and gentlemen, I told you that it was not all doom and gloom. Thank you, Dr. McMorris. You hit the nails, all of them, right on the head. Ladies and gentlemen, he gave us another way of surviving earthquakes. He spoke to the International Building Code. I would also, I know that he also spoke to, our local codes and how we have been dovetailing into that. Then he spoke of some of the gaps that exist because we have the code. We have the code. We use the code. But do we always adhere to it? And herein lies some of the gaps. He went on to speak about design criteria and the fact that the design criteria, yes, is risk-based. There are facilities that will not require as much input as others. And we talk about medical facilities, hospitals, other critical infrastructure. We should be able to continue to perform an operation inside of the surgery while an earthquake is taking place. But we have to build for that. We have to design for that. It is interesting, though, that Dr. Morris, spoke about the fact that we have, yes, robust building codes, but gaps do exist. Ladies and gentlemen, we're going to have to get to the stage where we accept that we have these gaps and we must now plug those gaps. The matter of continuous education happens in so many other professional fields. Why should it not happen in the field of structural engineering? And of course, you mentioned how well, relatively, we did for such an earthquake. And true it is, I would have been a part of or listened and heard some of the reports which you brought back, especially across the campus, that when we saw, or the pictures that were coming into us of damage, when we looked at them, many, most of them, non-structural. But even those non-structural damage, when somebody is evacuating a building and they see something coming down from above them, you don't tell them it's ceiling. They don't know and don't wish to know ceiling different from roof. And those very pieces of ceiling material could also impact you. And so it takes us to, I think, the point that he wrapped up on, that there are so many non-structural items, systems that could seriously impact what we do and how we behave and whether we even survive an earthquake. These are some of the things, colleagues, that we're going to have to take a very serious look at. We know we live in an area which is seismically active. We're going to have earthquakes. What we must now commit to doing is to accept it, first of all, and build with that in mind. And we have the experts here who can assist us to do that. If you notice some of his slides, we're not just about Dr. Morris. He spoke about some of his local colleagues who know what is required and can do it. We need to allow them to do their job, do it properly, so that when, I didn't say if, but when the next one comes, we can manage. Thank you so very much, Dr. Morris, for that enlightening discussion. I know many persons on this in this forum would have breathed, some much sigh of relief at this time. And we're going to continue along that line, ladies and gentlemen, because at this time, we're going to look at that thing I mentioned earlier, the one that we keep forgetting, the impact that we keep forgetting might not be physical, but what about the psychological impact to natural disasters such as the one that we're now discussing, all shook up by earthquake? And to bring that to us, colleagues, ladies and gentlemen, we have Mr. Billett. He is a licensed associate clinical psychologist. He works in private practice, but also is a lecturer at the University of the West Indies, Mona. Much of his work, he says, involves helping persons across lifespan, managing their emotions, increasing self-awareness, and finding healthy ways of coping with challenging situations. I think all of us can relate to that. He has a special interest in forensic psychology. He also deals with issues like trauma, personal disorders, and this is a good association and a graduate member of the British Psychological Society. Please make Mr. Billett welcome. Your show. Thank you.
Good evening, everyone. Thank you. Thank you, everyone, for inviting me. Thank you, Major Davis, for that introduction. All right, so I was excited when I got this invitation because it's not something that we usually speak about when we're talking about natural disasters. So I'm going to shed some light on this.
Tech control, we're not seeing the screen yet.
I'm just loading.
Yes, and just to remind Kevin that he has a lot to answer to, and Simon, a number of questions are coming your way also. Yes, please go ahead.
Okay. Are you seeing?
Yes, we're now seeing your slide.
Right. Okay, great. All right, so I want to start with this. Now, when we are faced with various challenges, big changes, problems such as natural disasters, we go through a process. We go through a process where there's a disruption, changes are happening, we feel pressured, and so that comes with the presence of uncertainty, continued pressure, trying to figure out what is going on, what should we do. There's a lot of unknown factors as well, and so that comes with anxiety. Right? Then we continue into a space where we're asked to adjust and accommodate, which is not the easiest thing for many of us to do. And so that comes with resistance. That resistance, you're fighting against the reality of the situation. So it's basically it's a situation where life is not what you want it to be, or your reality has changed, but you're not welcoming, or you're not open to that change, or you're finding it very difficult to accommodate, so that there's this conflict that you're having, and so that leads to stress. Now, should this stress continue for quite some time, or if it's deemed toxic stress, then it could lead to possible mental health challenges. And so in these situations, at some point, we will have to reroute and embrace the situation we're in so that we can learn, adjust, adapt, and make the necessary changes. Now, in preparing for this presentation, I thought it best to utilize this model, the disaster ecology model, because it is a beautiful conceptualization of how or mental health or mental processes are impacted by what is happening within our environment. So the disaster ecology model speaks to a disaster being categorized as an encounter between forces of harm and a human population in harm's way, influenced by the ecological context that creates demand exceeding the coping capacity of the affected community. Okay. Now, basically, what this is talking about is that we are in a zone, as we've been hearing all evening, where we have earthquakes, there are hurricanes. As a result of heavy rains, we will have floods, and there are other things that will happen that are categorized as natural disasters. So this model integrates the physical and the psychological. And so now it allows us to take this greater look at the different impacts as a result of the natural disasters. So our entire lives are affected, actually. So we have the disasters where so that would lead to further hazards. We have various losses, our lives are changed. So work is disrupted, school is disrupted. We may lose a loved one. We will lose electricity, or may lose electricity at certain necessities. As I said, one disaster could result into another, so we could have heavy rains or even an earthquake that could have led to landslides, buildings cave in, that sort of thing. That will therefore impact the individual and the family structure. That would impact the community as well as a society as a whole. And it is deemed that more persons are actually affected psychologically than physically when we take into consideration natural disasters. And so as a result of these challenges, or these effects rather, our livelihood can be disrupted. So we have this model, the Maslow's hierarchy of needs, where it is said that we start out with the meeting of our biological and physiological needs, our basic needs and our safety needs, right? And then when those are satisfied, we are more inclined to step into satisfying our need to be loved and belong to other groups, other people, even within ourselves, because then we'll grow even to build our esteem needs. And hopefully we'll reach to a point of self-actualization. Now, when we have the presence of natural disasters, that puts a threat on our biological needs, getting safe water to drink, healthy food. The air could also be contaminated depending on what happens. And our safety needs, because our security, our shelter, stability, all of that is now threatened. So life as we know it is changing or will change. Okay? And so that will impact or the potential of us wanting to even care about social connection. And it may even have an impact, if we're not careful, on how we see ourselves. Because then once we were independent, we're family oriented, and we're able to, take care of everybody, take care of ourselves, engage in our hobbies, do what we like. But because of a severe earthquake or a Category 5 hurricane, we no longer have these needs to stand on. And so we have to go start back from the scratch. And so we may see ourselves as less than, because we may feel as if, okay, well, it's a situation where you do not have these things, so you have to turn to somebody to ask for help. And that may have an impact on how you now see yourself and how others will see you. Now, it's a stressful situation, and if we really look at it, what the science tells us is that stress has an impact on our brains, right? And these are just three of the many components that will be impacted by especially prolonged stress. So you have the prefrontal cortex, decision-making, working memory, self-regulatory behaviors, such as your mood impulses, the hippocampus, where memory resides, the ability to regulate your mood, the amygdala has to do with anxiety, fear, and aggression. So the prefrontal cortex, it helps to regulate by shutting off the stress responses. The hippocampus contributes to that shutting off as well. And the amygdala will turn it on. So in stressful situations, especially if it is prolonged, the brain is so wired that the amygdala is constantly on the go, and anxiety, fear, and aggression takes precedence over everything else. And that's not what we want. We want to learn how to regulate. And in the context of a natural disaster, because we're so stressed and life as we knew it is no longer, we are in a constant state of arousal, which is not the healthiest thing to do. Now, it can go on into trauma because we now probably will step into a space where it was a traumatic event. It was an event where our life flashed before our eyes. We saw our end coming. We felt so scared, so threatened that we start replaying. We start having this deep-seated fear of what else is there to come. And so our responses could be, we want to fight, we're constantly irritable, angry, we're moving towards dangerous situations, we want to flee the flight, and so there's a lot of anxiety and you're avoiding certain things, so you may not even want to go into a particular building again or go into a particular area again. You freeze. The event happens, so like with the earthquake the other day, persons didn't know what to do. They were stuck. They were legit frozen, right? And then we have the fun. Persons who are people pleasing, they avoid conflict, they have difficulty saying no. And so these responses are meant usually, or they are meant to meet the demands because you're in survival mode at that point when a traumatic event occurs. We perceive danger, we perceive threat, and so we will utilize, or these responses actually they just kick in naturally. But for some persons, they're kind of stuck in these phases or these they perceive many situations as threatening, and so these responses come very frequently. And so if persons are traumatized, then, and it's not dealt with, we can have some serious impacts of trauma, as I have here. So we have the flashbacks, the vulnerable feelings, a lot of anxiety. There could be withdrawal from social spaces, feeling shame or guilt, difficulty sleeping, numbness, and it goes on. And these can even continue into the development of mental illnesses, mental disorders. Adjustment disorder is one that comes off the top of my head. Post-traumatic stress disorder is very real, right? It could also lead to depression and anxiety disorders, and it varies. Now, taking it a little bit further in terms of how the body processes or responds to trauma or even stress, just to sum this up, usually we would start out with in a very calm mental space, and then we would perceive a threat, and then we get activated. Negative thoughts will come. We are continue seeing the threat, or we encounter the threat. The brain is registering what is happening. If you've had a childhood trauma, the threat can trigger those feelings, thoughts, memories as well. So it's not just what is happening in the moment. It's not just the earthquake possibly, or not just the flooding or the fire or the hurricane, but everything else that has happened in your past could come flooding back, and you're dealing with all of that. So when you're faced, because children are human beings too, and they have their own minds, they have their own emotions. Sometimes their emotions are bigger than their bodies, but their emotions are their emotions, and so you just need to give them space. Hence, I have create safe spaces. A safe space is not necessarily a physical space, but it's the opportunity for persons to share and be heard. And at the very last one I have, you may need to see a professional to speak to that person. And so I am attached to Dr. Katie and Morgan and Associates, and which is where I see my clients. I'm representing them today, as well as College Journey, cultivating advocacy, healing, learning experiences. This is an organization that is looking at is trauma focused. We're interested in learning, researching about traumas, helping persons who have had traumatic experiences, and communities and organizations, and to help to have Jamaica and the Caribbean become a trauma-informed society, really. So how can we help others, work through their trauma, one, but also prevent the trauma from continuing? Now, you can also reach out to the Jamaican Psychological Society, whose members are psychologists. Yes, in Jamaica, across the Caribbean, and also internationally. There are a list of persons there that you can reach out to across the island to say, I may need some help for myself or a loved one. And what I'll ask you to do, though, is to ask the individual if they are licensed with the Council of Professional Supplementary to Medicine, CPSM. And if they're licensed or being supervised by someone who's licensed, then you can engage their services. And yeah, it's all about preparation, but also, what I'd say to you is, yes, it's all about preparation, but if you're doing it and it becomes habitual, then when the disaster happens, you'll know instinctively what to do. Thank you.
Sir, I want to thank you so very much for the enlightening presentation. After Gilbert, I kind of lived it for a number of years. It just kept on going over and over in my mind. I was in the military at the time, and I was deployed the day after. And I saw some things that persons would not normally see. I saw things firsthand, and it just kept living on and on. I lived 1993 earthquake over and over again. And then came last Monday. And then this Monday came, and I wondered if something was going to happen again. It is real. It is very real. Ladies and gentlemen, we heard about what happens after the shock. We heard about what happens after the impact. And, Mr. Billett was not just focusing on earthquakes, but just about any kind of shock that could reach an individual. He spoke to us about the anxiety that comes in, the resistance that comes in, the stress that comes in. And basically, your whole life and the way you run your life can change in an instant. The Maslow's hierarchy of needs went out the window at some stage, and can go out the window many times, because of how the particular event could impact you. It is very important, though, and I'm very happy that inside of all of that, you were able to bring to the fore the coping mechanisms that we need. And yes, true it is, we need some of these after shocks of this nature. And many of them we actually need right throughout life. In fact, for a moment, I was wondering if I need to take a year off, because you're telling me of all the things I need to do, like the self-care and all of that. And it is interesting that it's coming out, and persons need to understand that this is important. It is also important, ladies and gentlemen, that when we get to a point where we realize that nothing is working, things are not changing, you're living that day all over and over and over again, it may be time to seek professional help. And don't be afraid to seek professional help. Do not be afraid to seek professional help. Thank you so very much, sir, for your presentation. Colleagues, we are now at the point where we open the floor for questions. And I have about 20 here already. They're mainly pointed at Simon and Kevin. How soon after an event does the earthquake unit, how soon after can you send out the information on the earthquake? Kevin?
Well,
and how can I sign up to get alerts from the earthquake unit?
So it depends on the event itself. Each event is different, as well as the number of stations we have working at that point in time. So it varies. Our response time varies. Again, although we run continuous monitoring systems, we do not have a 24-hour operations. So you would find that sometimes if it's beyond office hours, it may take some time for us to then mobilize to get an official bulletin out.
And colleagues, we do know that, and ladies and gentlemen, all we do know that it did cause some amount of, can I call it some controversy in the last event, where we would have gone to social media. We got a particular reading from social media, and then came the official reading. But true it is, and I'll speak to it in a little while, that we do have some challenges. We do have some challenges. There are some things that we're still working on, and Kevin was honest enough to tell us what some of those challenges are at this time. How many, I know up to the time we met at that National Disaster Response Conference on the Tuesday morning, we had about 55 aftershocks. How many aftershocks have we had since? And are they still taking place?
We have had aftershocks since the event, and we are currently processing. Our analyst, Raymond Stewart, he's trying his best to process what we have already collected. So we continue to record small aftershocks. And of course, because of the number of events that we have, more than 70 that has been located, it will take us some time to really get through all of it.
Thank you so much. Simon, I'm sure you're gonna take delight in responding to this one. To the best of your knowledge, are fault lines and location, those kind of locations, taken into consideration when major infrastructure, such as highways and so on, are being built?
Interesting. I would say that is one of the problems we have, is that the geological maps that exist and that are available at the present point in time are labeled as, and if people have seen them, they're usually labeled as provisional geological maps. And some of them are well founded based on actual geological mapping, and others are based on aerial photographs. Now, sometimes that's good. Sometimes it's not that good. I think that we can actually look very carefully at, recent infrastructure that's been put in. And I would particularly think about the North-South Highway, where we had the basically highway going in there. We had Boyers, basically a company from France, building a highway, and that was built on the basis of maps which were not useful. They came afterwards to me, asked me to look at it. I looked at it. I went and told them. They flew in a series of people who then said, "Oh no, no, you can't build through that," and the company left the island. So no, we're not very good at planning. We're not very good at planning at all. And really what we now need to be doing is to plan properly. And we're not better. We're no better at it. We still use these very provisional maps. As you know, Clive, I've produced a new set of maps, and these are based on geological mapping. And these are going to be in the public domain in the next year. If you are spending that many millions of US dollars building a road or building anything else for that matter, why don't you pay a few $1,000s and get a proper geological survey so you know what you're dealing with? Make it work, rather than having to spend 50 million US dollars because you get it wrong.
Thank you. Thank you. Yes, thanks a million. Thanks a million for that one. Thank you so much. I think the next one goes to Nicholas then. Nicholas, will the new high rises survive a stronger earthquake? And I think the person posing this question is making reference to the proliferation of high-rise structures in the city of Kingston.
Well, it's difficult to comment on that without having any technical information on the designs of those structures. But as I've alluded to in my presentation, the building code is robust. If engineers are registered and they abide by the building code and the provisions of the building code, if they detail their structures accordingly, if they ensure that their lateral force resisting systems are substantial enough for what is required, then I see no reason why they can't perform well. If geotechnical surveys are done to support the information that is required, then I see no reason why they can't perform well in the earthquake.
Thank you. Thank you so very much.
Clive, could I just come in there and just ask a poignant question is, how do people know that these things have been built in an appropriate way?
Well, that's where quality assurance comes in. There has to be quality assurance on the design side, on the construction side, and from the authorities. So
yeah, the approving authorities, right?
Yeah. Authorities. So if there are any
so if I want to go and build, buy an apartment in one of those things, how do I know that?
Well, we are all charged, with the responsibility to design these things to these standards and approve them to these standards. So it is a responsibility of the building professionals to stick to the standards that are the laws of the country. The National Building Code is a legal document. So at no point should we be violating those things.
Thank you. Thank you. Thank you. Thank you so very much. I don't know. I'm checking my other device here to find out if there are any other questions at this time. Are there any other questions from the audience? Oh, no. Okay. Okay. Therefore, ladies and gentlemen, I think we are just at the end then of this program. Let me first just say a big thank you on behalf of the deans of the Faculty of Science and Technology, the Faculty of Engineering, and the Faculty of Social Sciences for pulling us together like this for such an important event. Colleagues, I did mention that these events will happen. I mentioned that we'll react. We need to know what's behind the phenomena. We need to know why they happen, how they happen. We need to know how much the damage that we see in other parts of the world. Are they preventable? Are there steps that we can take to mitigate against them? And also, I did mention, what about those of us who survive? How do we now cope? How do we now manage these situations? And colleagues, to the best of my knowledge, based on the notes that I took, we got some good answers this evening. Jamaica has a very robust seismic network. It's managed, of course, by our earthquake unit. The earthquake unit monitors, collects data, collates data, cleans data, and use that data to inform the respective stakeholders. I must emphasize, though, just adding a plug there for Kevin, we need partners. We need partners. We have some way to go. We want to build out that network. We want to improve on what we already have for the safety of our people. Simon gave us in no uncertain terms that we are in a country that is seismically active. It is that way now, and he expects it to continue to be that way. The active faults that we now have equate to a vulnerability. We must remain prepared. When we turned the page, we then recognize that we can actually build for earthquakes. We recognize that we can put steps in place, recognizing where we are, recognizing the risks that we have. We can actually construct properly to manage those. We have codes, and I do know that we're falling down many times. Not with the codes. The codes are good. It is the implementation. It is the monitoring of the codes to ensure that persons build accordingly. We know that we design based on risk, and we don't believe that every structure has to be built for an 8. We don't believe that in the case of hurricanes, we don't believe that every structure has to be built for a 5. However, we do know that we have to build in order to manage the risk. The gaps exist, and I am sure that based on where Nicholas sits at this point in time and where he continues to sit, we are moving forward. We're going to get the professionals in the field, and we're going to get the professionals where we want them to be. We're not, they call us third world, there's nothing third world about us. We're as first world as any other, and we can do it. Ladies and gentlemen, it is not an easy road. And we do know that when these shocks come, we have to be able to process the shocks. We have to be able to manage the shocks. And as you reminded us in the last bit of your presentation, I cannot, as a father, crumble in front of my children. But at the same time, I may need some help. We're going to lose quite a bit of our acumen. We're going to lose the way we operate. But we must recognize when there is trauma. And when there's trauma, we must reach out for the coping mechanisms that exist. No man is an island. No man